Hi, everyone. Welcome back to another virtual remote session of statistical models. Today, we're going to continue talking about simple linear regression, and specifically, we're going to start with correlation, and then we're going to talk about some prediction and confidence intervals that we can do for simple linear regression as well. To recap, last time I gave a brief introduction to an ANOVA approach for simple linear regression, as well as calculating and interpreting R squared, the coefficient of determination, using output from this ANOVA approach. And we also talked about hypothesis testing and different methods for doing that in general for simple linear regression. And here's about right where we left off. So the correlation coefficient, R, is a value that's bounded in general between -1 and +1. So this is probably one of the more common statistics or values that gets brought up in everyday language, I'd say, is talking about a correlation between things. So typically, it's sort of alluding to this value here, this correlation coefficient. And specifically for simple linear regression, we calculate this as the sine of the regression slope estimate times the square root of R squared, the coefficient of determination. So this is one formula to get the correlation coefficient, but there's many. And we'll see some of those in just a bit. So why is it R? I was wondering this myself the last time I taught this class. Despite having taken many, many regression classes, I never actually knew why we used R for this value. Seems like C might be a better letter to use since it's the correlation coefficient. But the reason R is used is because of this person, Francis Galton, who has one of the first documented uses of regression in general. And so he liked to use the letter R to denote this due to the words reversion and regression. So there's a little factoid for the day here. So R is the sample value. So when we have just a finite set of data, just one data set, we use R to denote the correlation coefficient. But rho, in general, we use to denote the population correlation coefficient, which is typically unknown. So, for example, we could look at the correlation between the height and BMI of all Augsburg students. So that would be denoted with rho. And if we just had a sample of just, say, 20 Augsburg students, and we looked at the correlation in that one sample between the student's height and BMI, we would denote that with R rather than rho. So that's just a little bit about the correlation coefficient. Another useful equation for getting it, if we have other values such as the estimated slope, is to use this equation here. So we have the estimated regression slope is equal to R times the standard deviation of Y over the sample standard deviation of X. And the formula for the standard deviation, the sample standard deviation, is sort of this ugly looking thing. It represents the amount of variability in the Y values here, for example. I won't ask you guys to calculate like this by hand. So don't worry about it, but it is good to understand this formula and understand how like R gives us this value. So we talked about some different hypothesis tests that we can do last time regarding the slope and the overall model. Now, a third hypothesis test that we can do is testing if the population correlation coefficient is 0 or not. And specifically, we test the following hypotheses. So we have the null hypothesis that the true correlation is 0, and the alternative hypothesis that the true correlation is different from 0. And to test this, we get a t-test statistic again. And just like before, it's a t-test statistic because it follows a t-distribution. And this one has n-2 degrees of freedom. So the formula here is the correlation coefficient r times the square root of n-2 all over this value in the denominator. So it's not really intuitive why this is the formula for the t-test statistic, but it's based on theoretical derivation, I think, by a guy named Ronald Fisher, who is well known for a lot of areas of statistics. So as I was just mentioning, we've talked about 3 different ways to test for a linear relationship between 2 variables now, 2 quantitative variables. 1, testing if the slope is 0 or not, using a t-test. Second way, using an overall f-test based on an ANOVA table. And then this third way of testing from a correlation coefficient perspective, testing if the true correlation coefficient is 0 or not. So these 3 testing methods are actually equivalent in that they will give you the same p-value regardless of which method you use, any of the 3. Specifically, the t-test statistic for the slope approach, number 1, and for the correlation approach, number 3, are going to actually be the same exact t-test statistic value. And for the f-test, the overall f-test for the ANOVA approach, it's just that t-test statistic squared. And this, again, is due to statistical theory, I guess. If this is more interesting to you, hopefully you can take a mathematical statistics course in your time in college. So I mentioned last video how there's sort of hypothesis testing approaches, and there's also using confidence intervals. In general, confidence intervals give you just as much information as hypothesis tests, but even more regarding the question you're trying to test. So I think they're in general better to use in practice. And I feel like personally, the field should move less, like in teaching, we should teach less about p-values and more about just confidence intervals, since they're more understandable and, like I said, give you nearly all the same information as p-values do, but more. But that's my view. But I still, it's covered extensively in the text, and I think it is still useful to know. But anyway, so here we're talking about prediction intervals now. So we've established that we can just obtain predicted values, y hats, given an explanatory variable x. But it's important to be able to describe the uncertainty in our predictions. So for example, if the Seahawks and Patriots, 2 football teams, were playing each other, and I predict that the Seahawks will win by 5 points, it might be important to describe the uncertainty in how much I think they'll win by. So maybe I'm confident that they'll win by between 3 and 6 points. But if I say they'll win by between 0 and 30 points, that's not as specific, not as useful, because it's such a wide range. So the amount of uncertainty in our predictions matter in terms of how useful our model is. So there's prediction intervals, which is for an individual value that we're making a prediction for. And then we also have confidence intervals for the expected value or mean of y, the response, which we denote with mu sub y, given our explanatory variable x. And so this is, again, this is different. A confidence interval for the mean response is different than the prediction interval for an individual response value. So it's important to think about which one will have more uncertainty associated with it. And they also have different interpretations in general. We'll talk about an example to sort of display the difference between these two types of intervals. But the answer is that a prediction interval for an individual response has more uncertainty in it. And we'll see why this makes sense sort of with an example. I think it will intuitively be easier to understand. So the formula from the textbook, confidence interval for the mean response value is this y hat plus or minus t star, which is that multiplier again that I'll always give you guys. It's typically 1.96 or about 2 times the standard error of the mean response. And this standard error of the mean response is given by this ugly looking guy here. This is the standard error of the regression again, going back a bit. And then we have this lots of stuff going on under here, under the square root here. So this is n, the sample size, the explanatory variable x here, which is a single value here that we're wanting to get the confidence interval for the mean response for. We have the average explanatory variable in our whole data set, x bar. And then here's this summation over all the predictor explanatory variable values. So a prediction interval is nearly identical. But if you look very closely, the 1 over n inside the square root here is different. It now has a 1 plus 1 over n as this term here. So some extra, a little bit extra added on to the standard error for the interval that we're calculating here. So prediction intervals in general will always be wider than a confidence interval for the mean. So that's a key relationship again. A prediction interval for an individual response will always be wider than the corresponding confidence interval for the mean response. So let's consider an example with some real world data where we'll look at calculating these intervals. And we're going to load this NHANES National Health and Nutrition Examination Study data set, which is a longitudinal data set again, consisting of public health and demographic measures recorded on 5,000 people in the US. And we got to take a look at this in our activity actually last Friday, so you guys are a little bit familiar already. So in this example, we're going to look at the relationship between people's age in years and their measured systolic blood pressure, measured in millimeters of mercury, Hg. So this is cool. This is actually real world data measured on people. So usually we can just use the plot function in R. I wanted to show a different way you can create a scatter plot as well, just so that you know there's options. There's always several ways to do things in R. Some people like ggplot for creating plots, data visualizations in R. It's a bit trendy, more customizable, maybe more fun, some people would say, who really like R. But yeah, I wanted to show you guys how you can the R code for making a scatter plot using ggplot as well. So here's a scatter plot displaying the relationship between people's age in years on the x-axis and their blood pressure in millimeters of mercury. And notice again how I label the axes nicely. I don't just keep the variable names as they were recorded in the data set, and I make sure to put the units, label it with units as well. Those are always important on data visualizations on plots like this, as well as an overall title. So it's important to think about, what do we notice, what kind of relationship is going on here? Does it appear to be linear? So looking at this scatter plot, so one, we can see that people's ages look like they roughly start at like 10 years old or so here and go all the way up, and it looks like they have a hard cutoff at 80 years old. So it appears that in order to be enrolled in this study, people had to be 80 years or younger, and also they couldn't be too young as well. So there's sort of an age cutoff in our data set. This is important to keep in mind as we do inference regarding different variables and things, making these conclusions. It's important to know the type of people that you have stuff measured on in your data set. Keeping that in mind, in general, we see that as people get older, their blood pressure looks like it tends to increase on average. And that's what we would expect right in real life. As people get older, their blood pressure gets a little bit worse. And in terms of linearity, there's a lot of scatter, a lot of variability, which is what we expect in measurements on real people. But in general, I'd say it looks fairly linear. It's certainly not a very clear quadratic relationship or oscillating too bad in any way. So I'd say a linear relationship appears reasonable here. So let's go ahead and fit a simple linear regression model and assume our assumptions are met. Ideally, we would plot the residual plots, histogram, stuff like that to check the model assumptions, but we're just going to get into the fitting the model right away here. So using the LM function, we are modeling blood pressure as our response using age. So this makes sense, makes more sense here in that we probably wouldn't be as interested in predicting someone's age given that we know their blood pressure. Usually it'd be the other way around. Like, we want to know what type of blood pressure should we expect for someone given their age. That would be more helpful for doctors. Doctors usually don't need to, guess, oh, I just have this patient's blood pressure, but I just need to know their age. I need to estimate their age. So anyway, so this is a setting in which the response and explanatory variables sort of only make sense one way, more so. Printing our regression model output here, we have the number of complete observations, which was roughly 8,500. We have the regression estimated slope here, the y-intercept estimate, their corresponding standard errors, t-test statistics, and p-values. And our R squared, our coefficient of determination here, of about 26.4% or 0.264. So lots of information in all this output again. Continuing on using ggplot here for our scatter plot, I added this geom_smooth code to it to add the line of best fit for a linear regression. So it adds this blue line on top here to visualize this. So here we can see it sort of seems to capture this relationship in the data decently well. If you do try ggplot code, it's important to note that these pluses always have to come at the end of the line. You can't have, you couldn't have moved this plus, for example, over here to start the line and have nothing ending here. ggplot's really picky about the syntax and the way it is. Just as a heads up, that's a hard error to debug usually. So recalling all the way back to our ANOVA table, we had model degrees of freedom, and we also looked at what's the coefficient of determination. So here again from the regression output, this first value in the parentheses after this F, this is telling us our model degrees of freedom. So here it is 1. And that's actually always the case for all simple linear regression models. The model degrees of freedom is always 1. The second value in the parentheses after the F is the error degrees of freedom, which is equal to n minus 2. So here you can see 8,551 minus 2, that gives us this model error, this error degrees of freedom term. Oh, and I asked about the coefficient of determination is 0.264 here, or 26.4%. So interpreting this again, we say roughly 26.4% of the variability in people's systolic blood pressure is explained by their age in years. That's how we interpret the R-squared. Another question we can ask based on this output is if the coefficient, the slope for age, is statistically significant or not. So let's go ahead and test that here. So testing the slope, our hypotheses, so we're going to be using this value here. So this is our beta hat, our slope estimate, 0.439. And to test if it's 0 or not, forgive my handwriting, it's a little bit tough to write with a computer mouse, but we are testing if the true slope is equal to 0. Notice I don't put a hat in the null hypothesis because we're testing a question about the true slope, not the estimated slope. We already know what the estimated slope is exactly, so we don't have any questions about what that is. And our alternative hypothesis is that it is different than 0. So those are our hypotheses, and in words, we would say our null hypothesis is that there is not a linear relationship between age and blood pressure. Our alternative hypothesis is that there is a linear relationship between age and blood pressure. Okay, so that's stating our hypotheses. And to test this, we look at the p-value here. This is the p-value that's relevant here for testing if the true slope is 0 or not. And since it's less than 0.05, we say using a significance level of 5%, we reject the null hypothesis. In other words, we have evidence that there is a linear relationship between systolic blood pressure measured in millimeters of mercury and age in years. That's our conclusion in the context of the problem. All right, and then calculating a 95% confidence interval for beta 1. We again go back to the output here. We're going to use this fact that beta hat 1 is equal to 0.439. And we're just going to round that to 0.44. And to calculate a confidence interval here, we're going to do, so 0.44, which is just 0.439 rounded, plus or minus 1.96 is our t-star multiplier, times the standard error, which I am just rounding to 0.01. This is the standard error for the slope here, 0.008. And that gives us 0.42 and 0.46. So interpreting this, we say we are 95% confident that for every 1 year older a person is, their systolic blood pressure will be between 0.42 and 0.46 millimeters of mercury higher on average. Okay. So that's how we interpret the confidence interval that we constructed. And again, I rounded the 0.439 to 0.44 and this 0.008 to 0.01. All right. Sorry, I'm scrolling quickly. So now, we calculated a confidence interval for the slope. We can also calculate a prediction interval. And specifically for someone who's 20 years old or 100 years old, we can get a prediction interval for their systolic blood pressure, a reasonable range of blood pressure values we think they'll fall in. And so here's the R code for doing that. But it is good to think about when it's appropriate to make such predictions. So in general, the rule is you should only make predicted values with your model if the new X values that you're using, making the predictions for, are contained in the range of values of your data set. So for example, here, it's appropriate to make a predicted systolic blood pressure for a 20-year-old because our data set ranges from 10 all the way up to 80 years old. So that falls in that range of our observed values. But a 100-year-old person, we don't have anybody that's that old. The oldest person in our data set, looking back at the scatter plot, was 80 years old. So if we made a prediction out here, that's what's called extrapolation, or pretty much just making a prediction outside of your range of observed data. And this is not considered good practice. Your predictions could be off. In some settings, it might be reasonable. But the thing is, you can't assume, by doing that, you're assuming that this relationship continues to hold even farther out than we've seen for data, which might be the case, but maybe not. So maybe a good example of that is if you plotted like income or the amount of money that someone has and their age in years. That tends to increase as you get older, you're accruing more money, but at a certain point that likely plateaus or starts to decrease again, maybe. So you would get messed up or turned around if you tried to assume that relationship continued to hold that you saw in younger ages into the older ages. So extrapolation, not a good idea. So it's not appropriate here to make a prediction for someone with this high of an age. However, we do it for demonstration for the sake of this problem. So using R, we get the predicted values here. This is their predicted systolic blood pressures for a 20-year-old and then a 100-year-old, the corresponding standard errors of those predictions, and the degrees of freedom. So we can also calculate, instead of a prediction interval, a mean interval using R. And to do this, we change the interval option to say confidence instead of, I believe it was prediction. I believe it's prediction. And printing this using R, we have our predicted value again. And this is our lower bound for the mean interval, and this is our upper bound for the mean interval. So we interpret this interval as saying we are 95% confident that the mean systolic blood pressure of all 20-year-old Americans is between 108 and 109 millimeters of mercury. So this is the key distinction here between a prediction interval for an individual person or value and a confidence interval for the mean. So here we're just saying we're giving this range of values, which is quite narrow, because we're talking about the average blood pressure for all 20-year-old Americans. And we can be pretty confident about that if we've observed, say, a few hundred 20-year-old Americans in our data set. We can get a pretty good idea of what it'll be. But individual people still vary a lot more just from person to person. So a prediction interval, if we calculate that using the standard error value and the fitted value here, sorry, not using these values, but if we obtained a prediction interval, it would be much wider than this confidence interval for the mean. And we could reobtain this interval ourselves using the standard errors that I obtained up here previously. So if we use a t-star multiplier of 1.96 and then the standard error of 0.2308 here, along with this predicted value, so using these two values, and the t-star of 1.96, we can verify this confidence interval for the mean. All right. Oh, yes. Okay, I was right. And prediction is the option for the prediction interval. And so here we can see using R, we get a much, much wider range. So before, it only went from 108 to 109 for the 95% confidence interval. Now it's 79.9 all the way up to 137.9. So this range is so wide. And this is because this is just for a single 20-year-old American. Where do we expect their blood pressure to fall? 95% of the time. So this is different than what we expect the average blood pressure to be for all 20-year-old Americans. So it's sort of a subtle but key distinction. Interpreting this interval, we'd say we expect about 95% of all 20-year-old Americans to have a systolic blood pressure between the lower and upper bound values. And so that's it for interpreting and calculating mean and prediction intervals. Next class, we'll continue with more regression, another video on that. And Friday, as always, we will have our Friday coding session together. And as a reminder, homework 2 is due this week, Wednesday. So please make sure you look at that if you haven't had the chance. Thanks, and I'll see you guys again soon.